Hello everyone, my name is Huanle Zhang. I am a postdoc at the University of California, Davis. I was a PhD candidate when I did this work. My co-authors are Mohapatra from the George Mason University, Cheuk from AT&T Research Lab, and Prasant Mohapatra from the University of California, Davis. Our title is Slimmer, Accelerating 3D Semantic Segmentation for Mobile Augmented Reality. By definition, 3D semantic segmentation is a process where a given 3D input, such as 3D mesh or point cloud, is divided into partitions that share the same local properties. In this paper, we focus on point clouds mainly because of its simplicity and flexibility compared to 3D mesh. In the middle is an example where an indoor point cloud is segmented. 3D semantic segmentation is an essential building block of augmented reality. Here are several use cases. A user can move objects by changing the location of a table in a room without actually moving it, and visualize how the scene looks like without that table. A user can play with objects by shooting a virtual ball into the scene and watching how it bounces off different surfaces. A user can control objects in the camera view by turning off a lamp while making a gesture. A user can also merge objects into the virtual reality so that a user can both view the virtual world and interact with physical objects. In order to know whether mobile devices can support 3D semantic segmentation, we conduct the following measurements. We adopt a sparse curve net, which is the state-of-the-art model of 3D semantic segmentation. Sparse curve net is a sparse convolutional network which is widely used for 3D tasks. We use the ScanNet indoor dataset for scene segmentation. We run the pre-trained model on a Dell Alienware laptop and measure the inference time, memory usage, and accuracy of the DLN model. Our measurements shows that the DLN model needs 4.2 seconds and 2.8 GB memory for each point cloud. Our measurements result clearly shows that the state-of-the-art 3D semantic segmentation model is too costly for mobile devices. During our measurement study, we observed that the inference time and memory usage of the DLN model grow approximately linearly with the number of points in the input point cloud. Therefore, we simplify the input point cloud by reducing the number of points in it and run the pre-trained DLN model over the specified point cloud. Please note that we don't make any changes to the pre-trained DLN model. We only specify the input point cloud. This slide plots the measurement result. Figure A shows how the accuracy of the DLN model changes versus the specified point cloud. The performance at 100% simplification ratio represents the model performance without data simplification. We can see from Figure A that the IOU remains almost the same, even when only about 60% of points are used. Figure B shows the inference time versus the simplification ratio. We can see that the inference time is approximately linearly correlated with the simplification ratio. We plot the memory usage in Figure C, which also shows that the memory usage of the pre-trained DLN model is linearly correlated with the simplification ratio. Based on our measurement study, we propose Slimmer to accelerate 3D semantic segmentation. Slimmer is a generic and model-independent framework. Our idea is to remove a fraction of points in the input while keeping the pre-trained DNN models untouched. In designing Slimmer, we have two challenges. The first one is to determine a lightweight simplification method to specify the point cloud, and the second challenge is to segment the removed points from the original font-size input. This is because we simplify the input, and thus the results do not necessarily represent the original requirements of segmenting a given font-size point cloud. Therefore, we also need to assign labels for the removed points in the original point cloud. This slide illustrates the system architecture of Slimmer. Instead of directly running the DNN model on the point cloud, Slimmer specifies the point cloud and executes the DNN model on the simplified point cloud. After that, Slimmer segments the removed points using a KNN technique. Finally, Slimmer aggregates the DNN output for the simplified point cloud and the KNN output for the removed points to finish the segmentation. There are two core components in Slimmer. The first component is to simplify point clouds, and the second component is to segment the removed points. Let's look at the first component. In this work, we explore several representative simplification methods. Different simplification methods generate specified point clouds with different characteristics. We identified the following three simple but effective methods for specifying point clouds. The first one is random simplification. In random simplification, each point is independently kept with a given probability. Therefore, random simplification regards each point equally. The second one is grid simplification. In grid simplification, each point cloud is partitioned into grid cells of a given size. For a non-empty grid cell, a point is randomly selected among the points in that cell. Therefore, grid simplification favors sparse points than dense points. This is because only one point is kept, no matter whether the grid cell is sparse or dense. We change the grid cell to generate specified point clouds of different sizes. The third one is hierarchy simplification. Hierarchy simplification provides an adaptive simplification of a point cloud through local clusters, which recursively splits the point sets into smaller clusters until the clusters has less than a given size. Hierarchy simplification favors edge points than surface points and thus generates sharp and vivid point clouds. We change the target cluster size to generate specified point clouds of different sizes. The second component is to segment the removed points. The data simplification procedure splits points into two sets, points in specified point cloud and the removed points that are filtered out. Since we know the labels of the simplified point cloud from the DNN output, we only need to segment the removed points in order to generate a full-size segmentation. We propose to infer the label of a removed point by the majority label of its nearest neighbors that are in the simplified point cloud. Below are the algorithms of segmenting the removed points. First, we construct a KD tree for the simplified point cloud with complexity of ns times log ns. Then, for each removed point, we search its k nearest points in the KD tree. The neighbor searching for each removed point is fast, with complexity of nr times log ns. After we identify the k neighbors for each removed point, we assign the majority label of its neighbors to the removed point. The overall labeling procedure has the complexity of nr. The overall complexity of segmenting the removed points by our KNN-based method is NT times log NT. The complexity indicates that our KNN-based segmentation of the removed points is lightweight. It is robust against the simplification ratio, that is NSONT, and scales well with the number of points of the original 4-size point clouds. There is one configuration in our KNN-based segmentation for removed points, that is the number of neighbors K. It is straightforward to note that the smaller simplification ratio is, the more improvement of inference time and memory usage. Meanwhile, the accuracy is reduced. We propose a QoE that jointly considers the inference time improvement, the memory usage improvement, and the accuracy loss. Our QoE is a concave function to quantify system performance. Specifically, our QoE is based on the simplification ratio and is defined as alpha times TR plus beta times MR minus IR, where TR is the inference time reduction, MR is the memory usage reduction, and IR is the accuracy decrease. Alpha and beta are the weights for time improvement and the memory improvement. Since the inference time improvements and the memory usage improvements are highly correlated, we can simplify the QoE equation to lambda times TR minus IR, where lambda is the new weight to determine the importance of the inference time improvement over the accuracy loss. The definition of inference time reduction improvement TR and accuracy loss IR are shown on the right side. Before showing our evaluation results, I'd like to give some examples of slimmer output. Figure A is a 4-size point cloud, and B, C, D are a simplified point cloud that is 20% of its original size, specified by the random, the grid, and the hierarchy simplifications. The second row shows the DNN output for the corresponding point clouds. Big I is the segmentation ground truth, and figure J to L are the final output of slimmer. We circle the regions that are falsely segmented in the outputs. From the figure, we can see that first, the slimmer can segment the 4-size point cloud based on the simplified inputs of the point cloud. And the second, simplification methods affect the segmentation accuracy, as we can see that the areas of the falsely segmented regions are different. To evaluate slimmer, we conduct experiments on a Dell Alienware laptop. We use the ScanNet dataset to train a sparse ConvNet DNN model, and use the validation dataset of it to evaluate our system. We first evaluate the performance of the KNN, then we match the performance of the simplification methods. After that, we apply the QoE metric to explore the design space. In the end, we present the detailed overall system performance. There is one parameter in KNN segmentation for removed points, that is the number of neighbors K. We conduct experiments to determine the optimal K value that achieves high system accuracy and low KNN processing delay. The figure on the right side shows the KNN performance. The first column shows the difference K does not affect the system accuracy. The second column shows that K equals 1 has the least processing delay. Considering the accuracy and the processing delay, we adopt K equals 1 in the rest of the experiments. Different data simplification methods generate point clouds of various characteristics, and thus they affect the segmentation accuracy. In addition, each simplification method takes different amount of time to specify a point cloud. Figure A shows the system segmentation accuracy of slimmer when the point clouds are specified by the random, the grid, and the hierarchy. We have the following observations. First, the accuracy loss dramatically increases when the point clouds are specified to be smaller than 20% of the font size. Second, the grid and the hierarchy has smaller accuracy loss than the random when the simplified point cloud are smaller than 60% of its original size. Third, when the size of the simplified point cloud is larger than 20% of the original one, the grid simplification is the best. Fourth, when the size of the simplification point cloud is larger than 60%, the grid and the random has similar segmentation accuracy. Figure B shows the data processing time for the random, the grid, and the hierarchy simplification. We can see that 1. The random simplification takes the same time to generate a point cloud of different sizes. 2. The grid simplification takes a linearly increased time to generate bigger point clouds. And 3. The hierarchy simplification takes a significantly longer time than the random and the grid simplification. Since that data simplification consumes much less memory than running the IEEE model, the data simplification does not cause actual memory usage. We propose a system QE to investigate the impact of the simplification method, the simplification ratio, and the KNN configuration. Since k equals 1 is optimal for KNN, in this experiment we explore the QE for the simplification method and the simplification ratio. The first row in the figure shows the QE curve of the random, the grid, and the hierarchy simplifications versus the simplification ratio where lambda equals 0.2 and 0.7 respectively. We have the observations that first, the QE curves are concave, meaning that there is a simplification ratio that achieves the maximum QE. Second, different simplification methods have different QE curves for the same lambda. We can compare their performance based on their maximum QE values. And third, we use a black star sign to annotate the point of the maximum QE for all the simplification methods for each given lambda. The optimal simplification ratio is smaller for a larger weight lambda. The second row plots the actual processing time for the data simplification and the KNN and the reduction of DNN time for the combination of simplification method and ratio that achieves the highest QE for each lambda. We can see that the actual processing time of data simplification and the KNN is significantly smaller than the reduction time of running the DNN model on simplified point cloud than on full-size point cloud. In addition, we can see that as expected, larger lambda reduces more DNN running time because of smaller simplification ratio that achieves the highest QE. This table tabulates the details of the overall performance of SNIMA. We show for each simplification method the QE value, the system accuracy, the accuracy loss, the system inference time, the inference time improvement, the memory usage improvement, and the optimal simplification ratio. We change the weight lambda from 0 to 1, where 0 means that we only care about the accuracy, and 1 means that we equally treat the inference time improvement and the accuracy loss. We can see from the table that SNIMA is an effective framework for accelerating 3D semantic segmentation. For example, SNIMA reduces about 90% inference time and 9% memory usage with only 1% accuracy loss, using the great simplification with a simplification ratio of 69%. Or Slimmer reduces 29% execution time and 15% memory usage overhead with only 2% accuracy loss, using the great simplification with a simplification ratio of 69%. In summary, Slimmer is a generic and model-independent framework to accelerate 3D semantic segmentation for mobile augmented reality. By leveraging improved data simplification, it can significantly reduce the inference time and memory usage, while remaining high accuracy for the state-of-art DL models of semantic segmentation. The key advantage of Slimmer over the existing solutions is that it does not require any modifications to pre-trained DL models. In order to explore the design space, we propose a QAE metric to quantitatively compare different combinations of the simplification method, the simplification ratio, and the configuration of KN for segmenting the removed points. By adjusting the weight lambda, Slimmer provides various trade-offs between the inference time improvement, the memory usage improvement, and the accuracy loss. Thank you for listening. Any questions?